Good day, students. Today we are going to see one of the important chapter in the NEET physics session, which is thermodynamics. You know very well, thermodynamics birth gave not today or tomorrow, not today or yesterday or last year. It was birth was given to the thermodynamics almost 16th century, 15th century or 16th century. That is so 15th. What is this century? Current century now? 21st. So 15th century, 16th means almost. No, why are you blinking? 16, almost 5 century back. That means almost 500 years back. The main credit goes to just a simple introduction only. Then we'll go for this thermodynamics. The main credit goes to James Watt. So the James Watt, it's that's principle that we are using. You'll be using. No, everybody is using that pressure cooker, right? Pressure cooker. So the pressure cooker comes here. That's a main that is the main birth of the thermodynamics. So thermodynamics not it is not born today or yesterday. So it goes back very back. So that pressure cooker, what you are using. So what is the application of pressure cooker? What is the application of pressure cooker that you are using in your kitchen? It's meant for cooking. Okay. Why you want to cook? Why you want to go cook in pressure cooker then compared to other vessel? Fast problem. Something related to fast. We have to do it very fast. We have to not only the fast, more efficient. The heat that supplying is more efficient. The heat that you are supplying is efficient. Less fuel. So the time consumption. It will consume less time when compared to other vessel. If you take any other vessel, it will consume more time. So the time consumption, the time is very fast, so more efficient. It will be all the parts will be cooked at the random side. So this is a simple application of pressure cooker. So this pressure cooker was most invented. Now it's applying. It's almost it was started almost 5 century back. It's not started today. That's an example for pressure cooker. So now I am taking the pressure cooker. Okay, I'm cooking which is very toughest one. Which is toughest one is what? Meat, not the rice. Rice is different from meat because rice is easy to cook. Okay, meat is the one which you need to cook in all the sides. All the part of the meat has to cook it. All the meat of the master cook. So I am taking all the ingredients, adding to the meat, and taking the pressure cooker. Okay, it's let us assume it's taken 10 whistle. After I am switching off it. Okay, so when I switching off it, so when you will open the pressure cooker now? After releasing the pressure or after half an hour? After half an hour, not before that. So okay. So now once I am switching off the pressure cooker, immediately I am opening the pressure cooker. What will happen? It will burst. So there comes the first thermodynamics. So the thermodynamics helped you a lot. So nobody will open once I switch off it. It will either you will wait for certain time, like minimum 15 minutes. Before that it's not possible. Okay, so once it's you're taking 50 minutes means why you're taking 50 minutes? Yeah, you are allowing to cool the cooker. So you are allowing to cool the cooker, by which it says that the pressure is released. So the this is the thing. So why you care? What is keeping there? You are increasing the temperature. That is delta T varies. Temperature varies. Volume is kept constant. So when the volume constant volume, delta T is varies. That is T varies. If T varies means what? How I can write? Now T can be written as delta T. So T can be written as delta T. Why T can be written as delta T here? Because when let us assume you are taking half an hour. Okay, half an hour I am taking. When you started, what is the temperature? When you are switching on the gas, what is the temperature? room temperature. When you're switching on the things, the room temperature, which is T1. When you increase, after half hour, you know that 10 whistle came. Now you recognize, oh, everything is cooked. So you are switching off it. Now what is the temperature? T2, which is nearly boiling point of the water. Now everybody, for everything they will add water, which is equal to almost boiling point of the water. That's all. T2 minus T1. What is T2? Boiling point of water, which is near almost 100 degree. So when is what is the room temperature?
26.
Approximately 30. So T2 minus T1 equal to delta T, which is 100 minus 30, which is, so delta T difference is 70 degree. So then now pressure, when you increase, volume is constant. Volume is constant means the pressure cooker that you are using is constant, because the vessel will not change, volume will not change. If the volume is kept constant, which is V. So the delta V is constant. So the delta V is constant, delta T is T2 minus T1. Okay. Now go for pressure. Pressure is when you increase, when you are at room temperature, what is the pressure now? When at room temperature, before you switching on, when you switching on it, okay, that is at room temperature, that is P1. When you increase, after half an hour, what is the pressure now? That is, pressure is increased, that is P2. So the delta P is P2 minus P1. So here what is changed now? P2, delta P and delta T. No. What is changed here? I'm changing there. What is changed here? Changed here is delta P. Delta P, pressure is changed. Pressure is changed means delta P changed and delta T. So delta P and delta T is changed here with constant volume. Whistle of the constant volume remains same. It is not changed. It will not be changed forever. We change. So after switching, now after half an hour over, 10 whistle completed. Now what I am doing is, I am immediately switching. I am opening the pressure cooker, opening the lid. So what will happen now? Huh? What will happen now? Huh? So okay, what will happen? I am after, it will take half an hour. Okay, let us assume half an hour I am taking it. T1, T2, after T1 to delta T is temperature. The temperature T1, T2 is temperature difference, and P1, P2 is pressure difference. The 10 whistle completed. So I am switching off the gas. Now immediately opening the lid. Now what will happen? Pressure will. So what will happen now? Okay. So that's a common thing. It will burst. So what will happen? Water will burst to my face. So everybody knows that. So you have to wait for minimum 50 minutes or half an hour. Okay, let us assume you take half an hour. So half an hour cooking, half an hour cooling. So half an hour cooking, half an hour cooling. So 1 hour it takes the entire process. So now, so application is, just now I told you that's current, same thing you are applying, same cooking you are applying to ordinary whistle, it will take 3 hours. So 1 hour is different, no, half an hour. So half an hour, this is half an hour, that is 2 hour or 3 hour. So 3 hour means, so what will happen now? The current gas consumption is highest here. So here it is no consumption. So now this comes the pressure. So what is the technique behind in the pressure cooker? That comes the thermodynamics. So everybody knows that when you increase the pressure, the cooking will cooking will. So how are you increasing the pressure now here? By heating. That is delta T is directly proportional to delta T. Delta P. That is when the temperature increases, pressure also increases. So that concludes that delta T is directly proportional to delta P. So if I want to increase the pressure of the things. Okay, this is the part 1. This is for the pressure cooker or any. This is one pressure cooker. Okay. Now in the same thing, if the same thing, what will happen? So now this is the first point. Okay, this is the first point. That means delta T directly proportional to delta P with constant volume. Okay. Now, if I increase now I am increasing the volume. Delta volume is increases. So what will happen to pressure now? Pressure? Huh? You understand the concept here. Now I am going here. Okay? Now I am going here. That is over. That experiment is over here. Okay? That experiment is over. Now I am coming here. I am coming here. Same whistle I am taking it. Okay? Now what I am taking is, now the volume is not constant. It's not pressure cooker. Some other whistle I am taking it. Some other whistle I am taking it. I am heating it. So when I heating it, what will happen to the pressure? So temperature is increasing, which is delta T. But volume is changes. Volume is when T1 is there, V1. When T2 is there, after half an hour, something I am heating it. Okay, that is after half an hour. What is the temperature now? Which is T2. T2. That is T1 and T2. Okay, T1 and T2. Here, when T1 is there, volume is V1. When T2 is there, volume is V2. That is when the temperature increases, the volume is increases. Now what happened to the pressure? Huh? What will happen to the pressure? Pressure? Huh? Huh? Pressure will not increase. Pressure decreases. Because when the volume increases, the pressure that is kept in the volume, that will decreases. When the moment the volume increases, immediately the pressure decreases. This is the main scenario. This is what thermodynamics tells that. That means whatever you are going, I am going to temperature, pressure, volume here. So everything are interrelated. Everything is interrelated. So I am coming here. Now what I am doing? When volume increases, pressure automatically decreases. So this is what the thermodynamics tells that. Okay, when volume increases, pressure. Can you give example for this? Anything? Huh? No. Can you give example for this? Where the pressure decreases, volume increases.
Water tank.
Huh?
Water. தண்ணி நிறைய இருக்கும்போது நம்ம
Yes, it's not exact water tank, but okay, similar to water tank. Because we can take two options. We can take volume mix, because the water tank under which there is no water, so that one we can take as a volume of water. That is, volume of water is 0. But we increases when the volume of the water increases, what will happen to that? It occupied fully. Okay, volume on water. Let us assume the water has occupied the volume, enter volume. So when the volume enter volume, what will happen now to the pressure? Yeah, pressure decreases. It attains the 0. So this is some of the example. This is where the thermodynamics play into our day-to-day life. Okay. Now we go back to the steam engine. Steam engine, because you have understood now. Now we have understood how the volume varies, how the pressure varies with respect to volume with increased temperature. So the same thing was applied to the steam engine this pressure cooker was same thing around that period, 15th century something. They discovered that this pressure cooker. Okay, based on this pressure cooker only they discovered the steam engine. That's all. High pressure. At high pressure you are not at high. Yeah, I am coming here. Experiment number 1. I am coming here. At high pressure you are not opening it. Why I am not opening it? I am opening after half an hour. At the high pressure, what is the status of water? Huh? What is the status of water at high pressure? Yeah, vapor state. Liquid to vapor state. when it's in the high vapor state only, the material is burnt or cooked, very well cooked. So when the liquid is not, when it's not in the liquid state, it's in the vapor state. So that made the James want what to convert that pressure cooker to a steam engine. So what is a steam engine? Steam engine, not ordinary diesel engine. Diesel engine is different. Steam engine. You are aware, no? You are aware, no? Everybody is aware, no? What is steam engine? That is not available now. But it's still available. Where it is available? Huh? No, I can't hear you. Steam engine, it's not available here, but where it is available? Ooty, Kodaikanal. I think I teach to somebody, I think. I don't know which class. In Ooty and Kodaikanal, that's a hill station. Hill station, no official work, nothing. It's a tourism, and for tourism, no timing. See, no timing, nothing. No timing, no office work, nothing. It's a hill station. So they're still maintaining it. So you have to take coal, burn it. Water will be converted into steam. Water into converted vapor or steam. So when the high steam, what will happen? If the high steam is passed to a blade, what will happen? No. First high speed pass to a blade, the blade will rotate. The blade is connected to the wheel. Now what will happen to the wheel? Wheel will rotate. That's all. Once wheel will rotate, the engine will move according to that. So we can control the speed now. How we can control the speed? By controlling the pressure of the vapor. If the pressure is high, speed is pressure is high, speed is high. If the pressure is low, speed will low. Now we come to ordinary vehicle. Ordinary vehicle. Where? Our car. So I want to increase it. I want to increase means what will happen to? Accelerator. I have to press the accelerator. If I press the accelerator, more petrol will be passed. More petrol will be burned. So I will get the fast, high speed. I want to decrease the speed means? No, brake is okay. Brake is okay. So less acceleration. Brake is different. I want to stop the car for that brake. So less acceleration or more acceleration. So that's more acceleration means more petrol. Less acceleration means less petrol. So that petrol is burned. So it converted that petrol is burned, etc., to give the gas. So by which the blade is rotated. When the blade is rotated attached to the wheel, it will be fast. So this is what now we have to come for steam engine. Simple steam engine. So now you are well aware, no? Because you are taking coal, heating it. I don't know whether you have seen it. Have you seen the steam engine? No. Nobody has seen it. Nobody has seen it. There will be that design is slightly different. The engine will be there. The drivers in front of them they will have that burning part. So they will add coal every half an hour, every 10 minutes they will add the coal, and they'll add the coal and maintain that pressure constant. That pressure has to maintain constant to go the wheel, to get the speed of that wheel, to speed of the train. So like that it will move. So like that it will keep on moving. So if I want to add more speed, what will happen? More coal. So more coal, pressure will increase. That will convert more water. So the speed will be higher. So now it comes it's still available only in Ooty hill station and something, and in the museum. In museum nobody is using it. You can see it, but physically there you can see it, and people are using it still because it's a hill station. Okay, that's a main example for the thermodynamics. That's a foremost example of thermodynamics. Okay, so this thermodynamics So this is the thermodynamics, by which you can say is it's divided into 4 law. 4 law it is. 0th law, first law, second law, third law. So all the contribution tells that this is thermodynamics. From the thermodynamics, why you need 4 laws? You can need just 1 law, no. What is the difference between first law and second law, third law? No. First is 0th law, second is the first law, third is second law, fourth is third law. So all the things in all the contribution you are needing the 4 laws to put the foremost law. So why what makes the contribution that you need the 4 laws? You understand my question? You understand my question? You didn't understand? Repeat. Thermodynamics should tell only 1 law, okay? It is telling 4 law. Why you need that 4 law then?
Difference in pressure.
Huh?
Pressure difference.
No, that's okay. That's that's a science. I'm about science is different from psychology.
Using different places,
Huh?
using different things.
That 4 laws I will explain you. What is the difference between the 4 laws? I'm asking why you need for 4 laws. That is the main difference. What is the main difference? Why you need the 4 law? That means the first law and second law are different. Second law and third law is different. Fourth law, third law and zeroth law. Fourth law and third law is different. All are different. So all the difference are made means what is the main difference that could be the difference that made it difference. What is the main difference and what is the difference? Difference is the equation, first law of equation. So some equations makes a difference. What is the main difference? Surrounding. Your surrounding as put into various differentiation. For example, what is temperature in the land? Temperature in the land. What is average temperature of Earth?
40.
Average temperature is almost 40. Why? Because in Asia it is 30. Asia it is 30. In American continent it is 20. In African country it is 40. So overall average is 30, almost 30. This is for the land. But if you go to the straight to the sea level, what will be the temperature, average temperature of the any sea?
In some place of average
In any sea, there are plenty. How many seas are there?
5.
How many seas? So what are the seas? Sea. Sea. What is sea? I am asking about this biggest. First one is
Pacific Ocean.
Pacific Ocean, Indian Ocean, then
Third's Indian Ocean.
no, okay, something Pacific, Indian, then Bay of Bengal and Arabic Sea. No, Antarctica is different. Then, so various seas is there. No, what is the average temperature of any sea? But here the land will vary. Okay, land temperatures vary, but sea remains constant only. Okay, so what is the average temperature of sea? Average temperature of sea. Sea is made up of full of water. So the average temperature, whether you taking from Indian Ocean or Pacific Ocean, the average temperature of the ocean will be constant.
No, sir.
Huh?
Antarctica is cool, sir.
Huh?
Antarctica.
No, I'm talking about Antarctica. Then third is Antarctica.
Antarctica doesn't have sea.
Antarctica doesn't have sea. It's a sea. It's not. It's a sea. It's not a ocean. It's a that's different. Third one. Second one is I am going for Pacific Sea. Okay, sea and Indian Ocean. Something like Indian Ocean and sea. All are sea. Okay. So what is the average temperature of any water? Huh? It's a constant. It will be constant, and but in the land it will it will varies, but sea it will be constant because everywhere is water. Now again we will not go for Antarctica. Oh, that's a sea. No, that's ice. Ice we don't worry. You not good for us. Just sea and land. That is sufficient. So something they made a difference. That's because of land and sea. So that made them to put that because the same law which obeys in the land will not obeys in the sea. Sometimes vary. The fluctuation will vary. So that they thought that the surrounding will made that surrounding made the difference. So the difference you got, some difference you got, which is land versus sea. So that puts the that's made the difference. So based on that, now we go for zeroth law, first law of thermodynamics, second law of thermodynamics, etc. So in that first one is so this is going to take a lot of when we started.
9:45.
Oh, 9:45. Now it's almost 10:50. Half an hour over. Now only we are going to start the chapter. Okay. So first law of thermodynamics. So first zeroth law of thermodynamics. Zeroth law tells that you have to take two equilibrium, system, which is zeroth law says that two equilibrium. Two equilibrium tells that two equilibrium which is A, B, C. Three equilibrium A, B, C. In the C, A and B are both are equilibrium. That means both are maintained at the constant pressure. Constant pressure. Okay, something like constant pressure, etc. Constant temperature, constant pressure, everything. So if C is a system. C is a system that is isolated from that. When C is isolated from that, what will happen? C is isolated. So the temperature of A, B is different from C. When C is isolated. Now C is C is also in equilibrium with A and B. Now what will happen when C is in equilibrium with A and B? What will happen? Now the temperature becomes of A, B, C are almost everything is equal. So the two system I am taking. Okay, first system and second system. First system, second system. First system A, B are thermally equilibrium. Okay, but C is isolated. C is isolated means what? C is isolated. C is isolated means what? Separated. C is isolated means separated. That is, it will not have C will not contact with A and B. Now here I am going. Here I am taking two systems A and B. C is in equilibrium with A and B. That is, now when it's isolated means what is the temperature of A, B, C? A equal to B equal to T1 and C is equal to T2. So T2 is different from T1 because it's not in equilibrium as system is isolated. Now here it is A, B, C, all the three systems are in equilibrium. That means T1 A is equal to B is equal to C is equal to T1. Yeah, correct, T1. No T2 because all the temperatures are same. So this is the zeroth law of thermodynamics. They rotate panna. Then, so in the same scenario, now I am going for that is the mark. After that what? After that what?
First term.
No. Before that, is there anything? Because I will explain you now entropy. Entropy, delta Q. Okay, internal energy, delta Q, work done, everything now I will explain. Before that, is there anything? Nothing. Okay. So the first law of thermodynamics. First law of thermodynamics tells that delta Q is equal to delta U plus delta W. So what is delta Q? Delta Q is the heat supplied. Delta Q is the heat supplied. Delta U is the internal energy plus delta W. Delta W is the work done. So work done plus internal energy contributes the total energy you are supplying it. Okay. Now I am coming to This is a given equation. Now I am coming to the first law of heating the no cooker. I am taking the cooker now. So the cooker I am going for experiment. Now what is the work done here? What is the work done? What is the delta U? What is the delta Q? Delta Q is equal to delta U plus delta W. Simple. I am not going for the scientific term, simple term. First we see whether you understand my question now.
Yes, sir.
First delta Q is equal to delta U plus delta W. Delta W is the work done, delta U is the internal energy, delta Q is the heat energy supplied. Okay? Heat energy supplied. So now I'm taking the cooker, I'm putting the meat, I'm putting the water, etc. So boiling it for half an hour. Okay, now what is the delta Q here? Why you are blinking? Why you are blinking? Huh?
Heating supplies.
Heating?
Heat supply agadradhu delta Q, sir.
Heat supplying is a delta Q. That is change in the temperature. We are changing the temperature. When we switch on it, what is the temperature? T1. So after half an hour, I recognize it's cooked fully. So I am switching off it. Now it is, what is the temperature now? T2. So delta T is equal to T1 minus T2. That is first we are supplying some heat, which is equal to, here in the first law of thermodynamics, delta Q. This is what first I needed. This what first I would like to know whether you understood or not. So now you understood, no?
Yes, sir.
Then they also didn't understand. When I teach first of all, when I teach for the thing, they didn't understand. So then I converted this part of the things. Here, taking pressure cooker, they didn't understand what is the first law of thermodynamics. Nothing. Then I put this equal terms: steam engine, pressure cooker, everything. Then I have put simple things. Then after that only they understood. But now only they understood what is first law of thermodynamics and what is the difference between the steam engine and pressure cooker. So it's things goes like that. So then I recognized, oh, we have to put something normalized to what we are using the things. So then after that they understood. So now second one is internal energy delta U. Here it is delta U, which is internal energy. So here what it comes? Pressure is what? No, different. Delta Q is equal to delta U plus W. W is P into V. P into delta V. P into delta V is the pressure into volume. Volume is constant. Pressure is that applied pressure. Delta U is internal energy. Internal energy here is that heat retained. Heat retained. So the heat energy is that is retained is the delta U intelligence. So any intelligent energy that is the heat energy that is retained, okay, that is the delta U. So now you comes the delta Q is equal to delta U plus delta W. So when internal energy is 0, what will happen? Internal energy is 0. Delta Q is equal to delta W. Yeah, delta Q is equal to delta W. So delta W is equal to P into delta V. What is P into delta V? Pressure into change in the volume. Pressure into change in the volume. Yeah, so in the similar trend, now we go for specific heat of the substance. So specific heat of the substance. The specific heat of the substance is nothing but the amount of heat that is supplied to increase its temperature by 1 degree. So that did I give the definition? So the specific heat is given by the amount of heat supplied to the substance to change its temperature to increase by to increase the temperature normally by 1 degree 1 degree in increase. So delta S is equal to delta Q by delta T. Then now ideal gas equation. Ideal gas. Did I tell about the Charles law and Boyle's law? No, did I told you? No, for her. Charles law, PV is equal to nRT. Huh? Huh? இருக்கா எப்போ அப்புறம் வருதா? இல்லை சார்ல்ஸ்லாம் இல்லையே. Charles law and Boyle's law. இல்லையா? So okay, now what we see, specific heat capacity. So specific heat capacity is given by, for a constant pressure it is given by Cp and constant volume is by Cv. So Cp minus Cv is equal to R, delta Q is equal to delta U plus P delta V. So Cv is equal to delta Q by delta T by constant volume is equal to delta by U by delta T at constant volume. So Cp is equal to delta Q by delta T at P is equal to delta Q by delta T P plus P into delta V by delta T by at constant volume. That is, you are dividing delta Q is equal to delta U plus P delta V. So now if we divide by delta T, what will happen? Delta Q by delta T is equal to delta U by delta T plus P into delta V by delta T. So you are dividing that equation by delta T. So if you divide by the equation delta T, that is a constant volume. So Cp minus Cv is equal to R. That is the Cp minus Cv is equal to R. So now comes the, did you ever have Boyle's law and Charles law? No. What is Boyle's law? What is Boyle's law and what is Charles law? Charles law is the one. PV. So from this only that they derived the ideal gas equation. No, both of them come ideal man. He only derives the Boyle's law. What is the Boyle's law? Boyle's law tells that the pressure P is equal to P is equal to directly proportional by P is directly proportional to 1 by V. That is, when the volume changes, pressure is when a volume changes, what will happen to the pressure? Pressure decreases. When the volume changes, pressure decreases. And what to experiment I told in the first one. First one. First in the pressure cooker I am taking. What is that? Volume is constant. Okay, I am supplying the heat. So the temperature is increases. Temperature increases means pressure is increases. That is, P is directly proportional to P directly proportional to T. Now I am coming here. Okay, in the second experiment, pressure is so I am supplying the same temperature. Okay, now volume is increasing. When volume increases, pressure decreases. So the P is inversely proportional to 1 by 1 by V. That's all. Now you combine this both the equation. Okay. P is directly proportional to 1 by V. Here P is directly proportional to T. So now combine two equation. What I will get now? P is directly proportional to T by. You understood or not? No. No. See, I am going to experiment number 1. Okay. That's a pressure cooker. Just a typical pressure cooker. I am increasing the temperature. Okay. What will happen now? What will happen to the pressure? No, any one person. See, if everybody talk, I can't understand. Any one person. Any one person tell what will happen when I increase the pressure, when I increase the temperature, what will happen to the pressure? No, I can't hear you. That's what I'm telling. If everybody talk, pressure increases. Okay, when temperature increases, pressure increases. So what I can write here now? P directly proportional to T. P directly proportional to T. Here I am coming here. This is experiment number 2. What I am doing here? I am supplying the same temperature. I am increasing the temperature. Now volume increases. Now what will happen to the pressure? Decreases. So this one is, what is this one and what is this one? This one is the Boyle's law. This one is the Charles law. That is P is directly proportional to P is inversely proportional to 1 by V. So here it is P is directly proportional to T. Here it is P is inversely proportional to T 1 by V. Now I am combining both the equation. What I will get? Combine both the equation. Correct. P is directly proportional to T divided inversely proportional by V. So P directly proportional to T by V. Now I am bringing V to the opposite direction. So PV is directly proportional to T. Now I am removing the proportionality constant R. So PV is equal to RT. Then I am adding the number of moles gas present in that. So it will be N. So it will be PV is equal to NRT. PV is equal to NRT. That's all. So this is the equation. For this equation only, I explained you that experiment. 2 experiment I explained you in the beginning. So now I got the PV is equal to NRT. P is the pressure. V is the N is the N massa. Just so I explained, N is the number of moles of the gas. N is the number of moles of the gas. R is the gas constant. T is the temperature. That's all. PV is equal to NRT is the ideal gas equation. So almost, I think, when we started?
9:45.
Now it's almost 10:35. Almost we took 50 minutes to derive this ideal gas equation. Almost an hour, right? Almost an hour. PV is equal to NRT. This form the basis of all the thermodynamics. No thermodynamics, no world. No thermodynamics, no world. Because how no thermodynamics, no world? How no thermodynamics, no world? No thermodynamics, no world.
Everybody die with cold.
What is we take our earth, okay? Our earth. What is the constant of land versus sea? What is percentage of sea and what is percentage of land?
70% sea, 30% of land. 70% of sea is water.
And 30% is water. Okay? Land. Okay, land. So sea has more thing. The sea is now C is now?
No, high.
No, that's okay. That's so C. I don't want that percent. Just I'm asking about the percentage. Now C, the water. Water is stable. How water is stable? So let us assume water is not there. What will happen? What is the difference between Earth and Mars? Earth and Mars. Is there what is there? What is there in ice format? In ice format, under the ground, water is there. Water is present in the form of ice, not in the form of liquid. But here, water is present in the form of liquid. So, how water? What is present in the form of liquid? Huh?
Because the source of sun.
There also sun is Mars. Also the sun is there. See, Mars is our planet, right? Mars is next planet. For everybody, for almost 9 planets is there. 9 planets is there. All 9 planets are rotating around the sun. So sun is not for only us. For all 9 planets, sun is added. So the sun is liquid is water. Water is present in the form of liquid only in the Earth. But Mars also is present. Okay, in ice format, only in the ice format. Huh? Temperature is one of the factor. It's not about temperature, not only the temperature. Okay, let us assume Mars is coming here. Okay, Mars and Earth are. You go to Moon. Okay, similar to moon, Mars, ice also present, water also present, not in the liquid state, in the ice state. Huh? What? 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 Ice in moon also water is present, not in the liquid state, in the ice, solid. Yeah, that's ice. It's present in, so there are few few ice is present in the moon. So only here the liquid format is there. So how the thermodynamics related to it? What is the thermodynamics tells that? Delta Q is equal to internal energy plus W, delta W. So the delta Q is equal to delta U plus delta W. So if you maintain the heat energy that supplies, you have to make the constant internal energy plus work done. So if you maintain this, then only you will get you can say that because of that only water is stable here compared to Mars or Moon. So no, you leave out our Mars also. You can go to Moon. So any liquid is present there. What will happen? It will vaporize. It will vaporize and leave the atmosphere. So only in Earth it will be possible. So now you understand how the thermodynamics plays the dominant role. Okay. So now yeah, now we go for isothermal and adiabatic. Isothermal, adiabatic. Yeah, so isothermal means temperature is constant. Then adiabatic means no heat flow from between the surrounding. That is, heat will not flow from the system and surrounding. From the system, the heat will not flow. From the system to surrounding, heat will not flow. From surrounding to the system, heat will not flow. So the delta T is equal to, delta T is now in adiabatic, delta T. What is delta T? Delta T, T1 minus T2. You can take a system as T1 and surrounding as a T2, or system as surrounding as a T1 or system as a T2. Anything you can take. In whatever the case, delta T is equal to delta T is equal to T2 minus T1. That's okay. But what is delta T now? Delta T is a temperature. Just now I explained. I explained you past 1 hour. I am explaining you. Delta T is a temperature. Okay. What is adiabatic? What is adiabatic? What is adiabatic and what is isothermal?
Heat will not supply between the system and surrounding.
Heat will not supply. Heat will not supply means from the system the heat will not go outside. Surrounding temperature. From the surrounding, system will not come to the system. So that means delta T is equal to
Delta T equal to T2 minus T1.
delta T is equal to T2 minus T1. That the nomination that we are taking for your convenience I am explaining. Delta T is equal to delta T is equal to delta 2 minus delta 1 or delta T1 minus delta T2. Anything you can take, whatever you wish. That is not the answer. So delta T is equal to 0. Delta T is equal to 0. Why delta T is equal to 0? Because the heat that is in the system will not supply to the surrounding. The heat that is in the heat is in the surrounding will not supply to the system. So the delta T is equal to 0. This is for adiabatic. Now isothermal. Temperature is constant. That is T1 equal to T1 is equal to T2. That is the system present here, and this is the system. Okay, this is T1. Surrounding is T2. So T1 is equal to T2. That's all. So the T for delta work done for isothermal process, the W is equal to work done is equal to nRT ln V2 minus V1, change in the volume between V1 and V2. Okay, isothermal. For adiabatic, work done is equal to for isobaric. Isobaric is pressure is constant and isochronic is volume is constant. So what we had now know isothermal temperature is constant. Isobaric is pressure is constant. Then isochronic volume is constant. Then adiabatic no heat flow, there is no heat exchange. For isothermal process, work done is equal to nRT ln V2 by V1. Then adiabatic process nr T1 minus T2 gamma minus 1, which is gamma is the ratio constant. It's a constant. Then cyclic process. Now the heat engine. Yeah. Now the two types. Now comes the two types: heat engine and refrigerator. So what is the purpose? What is the purpose of a heat engine? Heat engine. What example we can take? Huh? Heat engine. What example we can take? Heat engine, I will take steam engine. I already explained you steam engine fully. What is the purpose? Take coal, heat it, water will change into vapor. Now high vapor will rotate the blade. The blade is connected to the wheel. Okay. Now if you increase the pressure, what will happen? Obviously, speed of the steam engine will increase. Yeah. So now we become thorough here. This is the principle of steam engine. This same principle is used here, and for work done and to become cold reservoir. That is cold reservoir. You know, hot reservoir is what? Hot reservoir is using the work done. Hot reservoir is using the work done. That you know. What is cold reservoir here? Cold reservoir I didn't tell. Cold reservoir. Cold reservoir is one which used to cool the thing. Okay. So steam engine is there. That used to rotate the blade. Okay. So the steam engine used to rotate the blade. So when it's become when it come out, What is that? I have to cool it. I have to cool it. How can I cool it? Huh? Using coolant. Using coolant. What coolant I will use? No. That is different. Refrigerator. Huh? Huh? Liquid nitrogen. You don't know. You need not go for that complicated liquid nitrogen. You can take ice. Okay. Just put ice. Now, what is the output of the steam engine? Output of the steam engine. Output of the steam engine. Huh? Output of the steam engine. Yeah, it has finished all the work done. That's all. The wheel is moving now. Once wheel is moving, immediately the engine will move now. Okay. So what is the output of it? Output is the steam. The steam coming now. That is the output. So if I put some ice, something like that, what will happen to the steam now? Yeah, it will become cool now. So the steam will convert it into water, liquid water now. So the steam will convert it into liquid water. So in presence of some ice. Otherwise it will stay as a steam only because of high temperature. So I have to put some steam in. So that is the cold reservoir. So what is the hot reservoir now? Hot reservoir, cold reservoir, then output in steam engine.
Output in steam engine is steam, sir.
No, output is not.
Vapor.
Vapor. Output. No, output.
Water.
Ice, water. Output is the energy. Work done. Work done is the input. Output, work done. Input is the one steam. Input is the one steam. Work done is the where the vehicle moved or the wheel rotation of wheel. Then output is the, what is the output? Input. No, output is the energy. Output is the energy by which the wheel is moved. Okay. In what is the input? Steam. Yeah, steam. Output is the
Energy.
input, output, work done. Input is the steam. Work done is the energy. That is by which the energy is supplied to the vehicle to move it. Then output is, output is the steam. Output is a steam. That output only we are putting in the ice. You are converting into liquid water. So now what we got it? Liquid water. So what is the output now? Output is a liquid water. Input is a, you didn't understand. Input, output, work done. What is the input now? Input is a steam. Yeah, how you got the steam? From the coal. From heating the coal from the water which is heating it, you will get a steam. Because the steam is the one that going to rotate the blade. It is not in the liquid format. It is not going to rotate in the liquid format. Okay, it is going to rotate in the vapor format. So the steam is the input, not the liquid water. You have to take liquid water and coal. You heat it very well. You know, right? So liquid water, you have to take liquid water, heat it, it will become steam. So the steam is the one that going to rotate the blade. So when I increase the pressure, what will happen? When I increase the pressure, what will happen now? The blade will rotate faster. When the blade will rotate faster, what will happen to the wheel of the steam engine? It will rotate faster. So that is the work done. So input is steam, work done is the energy. So that energy could be anything. It could be slow speed or high speed. So whatever, the driver will adjust the pressure. If the pressure is increases, the speed will also increases. Now comes the output. Output is the steam engine. The steam output is the steam. So when I put it in the ice water, what will happen? Steam will be converted into liquid water. That's all. So output is the liquid water. So input is what? What is input? Steam. What is the work done? What is output?
Liquid water.
Liquid water. That's all. This is what I am explaining you. This I already explained, no, when the start of the beginning. Huh? Okay, did you are clear with this?
Yes, sir.
Now, because now we going for refrigerator. Refrigerator is inverse of it. Inverse. Inverse is cold reservoir, and you have to do supply work done. You have to supply the energy that will convert into hot reservoir. That will convert into hot reservoir. So, what is a cold reservoir here in refrigerator? That will convert the, what is the work done? What is the work done? What is the cold reservoir? So that will do the output. Output, the cold reservoir work done is the electrical energy that we are supplying. Here what is the work done in steam engine? We are supplying the energy to move the wheel. Now I am coming to refrigerator. In refrigerator, what we are doing, we are supplying the electrical energy.
Output is electrical energy, input is heat energy, output is cold.
No, input is a cold energy. Input is a cold energy. Input is a cold energy ice. So input ice. So the output is the electric energy. So what is the outlet now? Hot water. Hot water. The output of the surrounding. No. What is that? Outside. You have seen anything? Did you see outside of the refrigerator? Side. If you get outside of the things, there will be like heat is produced. Heat is produced. That is because of this. So what is that? What is that heat? That is the output. There you can see like something like tube-like structure in the backside of the refrigerator. If you touch that, it will be very hot. So that is the output of the things. So this refers, both are reverse. What is that? Refrigerator and heat engine and heat engine and refrigerator are inverse. So now we go for heat engine. Okay, in heat engine is equal to total efficiency is equal to output by input. Output is the work done. Okay, input is the Q1, which is heat supplied. So the total heat supplied, total work done is total work done divided by efficiency. What is efficiency? Output by input. Okay, output is the one which the wheel is rotated. That is energy supplied in steam engine. I am talking about steam engine. In steam engine, output by input. Okay, what is the output?
Liquid water.
No, this is general term. Output by input. Output is a means that is how the energy that we supply, the energy done. That is the wheel is rotated. So that is total work done. That is the engine moved from one place to another. So that is total work done divided by total heat supplied, which is Q1. That is the total heat we have supplied is equal to total work done. So the total work done is given by Q1 minus Q2. So the efficiency is equal to now Q1 minus Q2 divided by Q1. So efficiency is equal to 1 minus Q2 divided by Q1. Okay, this is total efficiency. So in the same refrigerator, Q2 is alpha is equal to Q2 divided by work done. Q1 alpha is equal to efficiency is given by Q2 divided by Q1 minus Q2. That is alpha is equal to Q2 divided by Q1 minus Q2. Now last one we go for Carnot cycle. Carnot cycle tells that it is a complete cycle. It's a complete. This table is there, means it's a complete cycle. That is cycle one. First is thermal expansion, isothermal expansion. isothermal expansion, then stage 2 is 2 to 3 is adiabatic expansion, then isothermal compression, then adiabatic compression. What is isothermal compression? What is first isothermal expansion. What is isothermal and expansion? Isothermal temperature is constant. Okay. Temperature is constant. Okay. Then expansion means V1 to V2. That means expansion means volume is increased. Now second one is adiabatic expansion. Adiabatic expansion means what is adiabatic? Just now I told you. Heat is not exchanged. That is delta T is equal to 0. So delta T is equal to 0 means delta T is equal to 0. Then expansion means what? Expansion means what? Because already I expand by isothermal, which is V1 to V2. Now it is adiabatic expansion, which is V2 to V3. V2 to V3. Now third step is again. So this is isothermal expansion. Here it is adiabatic expansion. Here isothermal compression. Compression means what? Which is compression. Compression means volume is compressed. That is isothermal compression means what is isothermal? Constant temperature. So constant temperature, volume is decreased. Then adiabatic compression. Adiabatic compression. First is isothermal expansion. Second is adiabatic expansion. Then isothermal compression. Compression means what? Volume will decrease. Here then isothermal, then adiabatic compression. So again that is the here isothermal expansion means volume will increase. Adiabatic expansion means volume will increase. Now adiabatic isothermal compression means volume will decrease. Here it is adiabatic compression means volume will decrease. Finally it will reach the cycle 0. That's all. So now for this, what is the total thing is efficiency is total efficiency is 1 minus T2 by T1. Where T1 is the temperature difference. What is T2? T2 is the final temperature. T1 is the initial temperature.